Okay, 4.5 practice. Suppose 10% of adults belong to a health club, and 40% of those go at least twice a week. So the probability that they go to a health club and go at least twice a week, I want to multiply 10% times 40%, which gives me 4% of the time. So 4% of the population would go to the health club and go at least twice a week. Okay, the next one here, Forrest Gump. You never know what life's going to give you. Life's like a box of chocolates. Okay, I don't know if you've ever seen that movie, but you should see it if you haven't. It's an oldie, but it's a goodie. You never know. Suppose a candy maker makes 20 candies. Okay, so there's 20 candies. 14 have soft centers, so I'm kind of combining number 2 and number 3 together here. So soft centers would be 14 out of the 20, and hard would be 6 out of the 20. Now, if I pick another candy, it could either be hard or soft too, right? If I already picked a soft one, that would leave 13 out of the 19 as soft, and 6 out of the 19 as hard. If I picked a hard one first, that would leave 14 of the 19 to be soft, and the 5 out of the 19 to be hard. So in this one, they're asking us, what's the probability of getting a soft and then a soft? So probability of soft and then soft would be 14 out of 20 times 13 out of 19, which gives you this. Okay, number 3 asks us, what's the probability you're going to get one of each? Okay, so I could either get that through a soft and then a hard. So if I multiply this and this together, I get 22%. Or I could get a hard one and then a soft one. And if I multiply that and that together, I get 22% again. So the total amount of time that I would get one of each would be 44%. Okay, the next one, the computers for a company are made in either California, Texas, or New York. It says that California produced 40% of the computers. Texas made 25% of the computers, and the remaining 35% were made in New York. Of the companies in California, they made 75% of them are laptops, which means 25% of them would be the desktop. Okay, in Texas, %70 of them are laptops, and New York, 50% of them are laptops. So the desktops here would be their other 30%, and they're 50-50 in New York. Okay? So suppose we get a random, okay, so part A, here's our tree diagram. So find the probability that if I just choose a random computer, it's going to be a laptop. So a laptop will be here, here, and here. So if it's in California and a laptop, okay, I'm going to take 0.4 times 0.75. That gives me 30%. And 0.25 times 0.7, 0.175. And 0.35 times 50% is 0.175. Okay, so overall, okay, if I just pick a random computer, this is the overall. Okay, so if I would actually find all these out, so if I take 0.4 times 0.25, this would equal 10% of the time. 0.25 times 0.3, 0.075, and this would be 0.175. Okay, so if I add all these together, that's going to be 100% of my computers, right? 100% of the computers are there. But what's the probability that it's going to be a laptop? Okay, if it's a laptop in California, that's 30% of the computers. A Texas laptop was 17.5%, and a New York laptop was 17.5% as well. Okay, so I need to add those percentages together. And that gives me 65%. So I know that 65% of the computers made for this company are laptops. So the other 45%, if I add these other ones here, 35% would be desktop computers. Okay. Kind of goes with that. Okay, given that a laptop was selected, what's the probability that it was made in California? Okay, so the probability that it was made in California, given that it was a laptop. Okay, so we're going to look at only the laptops. So the laptops, we added those together, was 65%, right? 65% of them were laptops. And the ones that were made in California would be 30 out of those 65. So 0.3 divided by 0.65 gives me 0.46. So of all the laptops, 46% of those laptops were made in California. Okay, Roger Federer made 63% of his first serves in a recent season. When he made his first serve, he won 78% of those, okay? So either he's gonna first serve is in, or his first is out. Okay, so either they're in or out. So he made 63% of his first serves in. So that would leave 37% that of them were out. Now, it says when the first serve was in, he won 78% of the time, which means he lost the point 22% of the time. When he missed his first serve, he had to serve again. He won only 57% and lost would be what, 43%. Okay, so there's our diagram, tree diagram. Suppose you randomly choose a point in which Federer served. So we're just going to look at this. You get distracted before seeing his first serve, but look up in time to see Federer win the point. Okay, so we're given that he won. So given that he won, what's the probability that he missed his first serve? So what's the probability the first was out, given that he won the point? So first of all, we have to figure out what's the percentage of won. Okay, what percent of the time did he win his point? So I got to find these two here. So 0.63 times 0.78. So almost half the time he won his first point. The first serve was in and he won the point. Okay, 0.37 times 0.57 is 0.2109. Okay, if I add these two together, okay, so he won 70% of his points. Okay, so he won and won together 70% of his points. Okay, now given that the first one was out, if the first one was out, he won 0.2109 out of all those. So 0.2109 divided by 0.7023 gives us 30%. So if I know that he won, I look up and he won the point, 30% of those that he won were out the first time. The other 70% were in the first time. Okay, number 7. Okay, I don't know if any of you had to do this in the past or not, but many employers require employees to take drug tests. A positive test suggests that they have used illegal drugs. However, not all people who test positive use illegal drugs. the test could be a false positive, meaning they tested positive, but they really have not used drugs. A negative test result could be a false negative as well. But if they tested negative, but that was false, they really do use drugs. Suppose that 4% of prospective employees use drugs. Okay, so my diagram here. Either people use drugs or they don't use drugs. And it says we're going to assume that 4% use drugs, which means 96% don't use drugs. And then a drug test has a false positive, okay, of 5% and a false negative of 10%. Okay, so let's think about what these means. A false positive, okay, well here, let's put this in here. Either they test positive or they test negative. And these people will either test positive and test negative, okay? So a false positive means they tested positive, but they really don't use drugs. So they don't use drugs, but they tested positive was 5% of the time, which means 95% of the time, if they don't use drugs, they'll test negative, okay? And a false negative, so they get negative, but really they do use drugs, happens 10% of the time, which means 90% of the time, if they use drugs, it'll test that they're positive. Okay? So we're going to choose a random person and test them. Okay, we have our part A is there's our model. Part B says find the probability that the drug test is positive. Okay? So the probability that it is a positive result. So a positive result would be this area and this area right here. So we're going to use 0.04 times 0.9. And then down here, 0.96 times 0.05. Okay, so I'm going to add these together because I want this positive or this positive. And that gives me 0.084, which means 8%, a little bit over 8.4% of the time, if I just pick a random person, they're going to test positive. Okay? Whether they use or not, we're combining those two together. Okay, part C. Given that the test was positive, okay, so what's the probability that given that it was tested positive, that they actually use the drugs? Because that's what we want to happen, right? So if somebody tests positive, what's the probability they actually use the drug, okay? So this is going to be, we're looking at only those that are testing positive, which was the 8%. And of those, how many of them actually use? Okay, that was the 0.036. So if I divide those, I get almost 43% if I round it. Okay, this says, of all the people that test positive, which is a small amount, if you're testing positive, only 43% of those people testing positive actually use drugs. Not very good results, are they? Okay. So this test is probably not the most accurate. If people are testing positive, I want more than half of them to be using drugs. So this is not true. Okay, and the last one. A tree diagram can organize problems having more than 2 stages. The following problem for a charity of potential donors by phone. Each person is called as either a recent donor, a past donor, or a new prospective. So either people have given recently, or they're a past donor, or maybe they'll give in the future. Okay? At the next stage, the person called either does or does not pledge to contribute. So if once they call them, either they say, yeah, I'll give money, or they won't. And they'll give money or won't, or give money and won't. The third stage, finally, is if they pledge it, do they actually contribute? So of those that pledged, some will actually give and some won't. And same here for those pledges and those pledges. So we have 3 steps. Okay? So part A. Find what is the probability that a person contributed to the charity? Okay. Okay, so the probability that somebody contributed will be here, here, and here. Okay, so for this one, I have to take this times this times this. Okay, so we take the 0.5, they're a recent donor, times the 0.4, they're a pledge, times 0.8, actually contribute. Okay, so I'm going to actually write all this out. So 0.5 times 0.4 times 0.8, which gives you 0.16. Okay, the next people that contribute will be 0.3 times 0.3 times 0.6. And that was 0.054. And the third group that contribute are New Perspectives, that pledge, that actually contribute. And that's 0.01. So the total amount of people that contribute would be that 16% plus the 0.054 plus 0.01, 0.224. So a little over 22% of the people actually contribute to their fund drive.